project at the same time, or do they have to be?
That is a good question. I don't know if I can project. I think this guy just needs to change over. There we go. Yeah. Okay. Right. So here we go. The second game design class. This time we're going to be covering formal elements of game design and game balance. So if you remember from the last class, the formal elements are one of the three different types of parts of game design that we talked about. We have formal, dramatic, and dynamic. So formal elements are essentially the rules, the actual logistical elements of the game. We'll go into a little bit more detail in a bit about exactly what that means. But first, just kind of my favorite example of why the formal elements are so important came in one of my game design classes. We did an experiment where we had to essentially attempt to change an existing game. And one of the existing games that you could attempt to change was Connect 4. So what's really interesting about this, and maybe quit from this so this stops pinging me. What's really interesting about Connect 4 is if you look at the bottom row on Connect 4, there's 7 slots on the bottom row. What's significant about the number 7 is that it's not divisible by 4 2 times. So if you think about that, that means that you're competing for that space. It feels easiest to get a bottom row or like a horizontal row when you're doing Connect 4 because you just need to get 4 in an easy row, whereas like stacking 4 up is, well, still fairly easy, but diagonals are pretty hard and so on and so forth. So the point being that in both vertically and horizontally, you cannot have 2 people scoring. So there's scarcity there. If I start going for a bottom row score and you start going for the bottom row score, one of us is going to lose, just by virtue of the fact that 7 is not divisible by 4 more than once. So along the same lines then, there's other things that you can play around with this game. You can try making the board bigger, smaller. You can try having more players than just 1 versus 1. There's a lot of different ways you can play around with the different formal mechanics of this game. And what this experiment that we did in my game design class that I took was to play around with any of those elements, tweak any one variable you want, and see if you can make another fun game. And the fact was, it was really, really hard. Connect 4 is actually very well balanced in a certain way of thinking. It's very hard to make another game that's fun. It's kind of in a sweet spot. So let's take a step back and look what that means. So formal elements. Formal elements can be players, they can be resources, objectives, achievements, things that you're trying to shoot for, the world or the size of the board. And this is the size of Connect 4. The procedures, the rules, just all of these kind of innate, low-level laws of the game, so to speak. So to actually look at some of these one by one, players interact in a certain pattern. And again, I'm kind of shamelessly stolen some of these diagrams. Here are some of the different player interaction patterns that you can find. Single player versus the game, everybody knows that. That's, easiest, most simple to understand. There's examples here: Solitaire, Pac-Man, right. Multiplayer versus the game is kind of interesting. That's a cooperative game. The players are fighting alongside each other in order to beat the system. I actually just bought a board game this weekend that is a multiplayer co-op game. It's called Pandemic. I'm planning on playing it with my roommates soon. It's kind of interesting because I don't see a lot of board games that pull off the multiplayer co-op. It's in fact kind of a rare pattern. Does anybody think of any other multiplayer co-ops off the top of your head? I know Guild Wars. Sorry.
Some random Steam games.
Like yeah.
Theft, but like Heist or something like that. You try to rob a casino and each of you have a different role kind of thing.
Yeah,
Sure.
Monaco, yeah.
Monaco, random Steam games. Okay, yeah.
I've heard some similar sounding board games to maybe what you got, where you're like trying to escape from like a burning. You mentioned the escape from a burning building one, maybe.
Oh,
I heard that one from somebody else recently. Yeah. But also like keep a ship afloat, or like I don't know, like
yeah.
I think there's Space Team maybe is one too. Yeah.
Yeah, Space Team. That's the one we talked about last time, right?
Yeah.
It's a tough paradigm to balance too, to be frank, because players kind of like you can kind of in number 3 here generally assume that players are going to be of appropriate skill levels to each other, whereas when all of the players are playing against the game, it's really easy to accidentally create a game that's either way too hard or way too easy, or is just as bad, is too solvable. If you can solve the game, then it's boring after 1 or 2 plays. Unilateral competition, aka gang up. It's like tag or what have you. This is something that you don't see a lot. I think I've seen some games pull off unilateral competition before, like something like a defender versus attacker sort of paradigm, like maybe one person is defending a base and everybody else is besieging it or something along those lines. But it's a fairly hard one to pull off. Multilateral competition, so that's where everybody is fighting everybody. I think this diagram doesn't do it justice because it's not. Oh yeah, actually it does. Sorry, I was thinking it didn't connect everybody. But the notion that in Monopoly, Poker, Quake, you're on your own and everybody is an enemy. And then cooperative play. It's kind of interesting. I'm not sure what distinction they're essentially drawing between cooperative and multiplayer versus game here. Maybe less adversarial on the behalf of the game, or maybe you act as one party. Oh yeah, I think that's the differentiation, is that cooperative play, you act as one party against the game, whereas multiplayer, you each have your own strategies that you're employing against the game. And then team competition, which we know best from real-world games, or I don't like that phrase, but nonetheless, more classic sportsy sort of games, soccer, etc. Yeah, so those are the basic paradigms you can employ in game design. Resources. A few different examples here. Resources to me are one of the most fascinating concepts in game design, because resources are what create this sense of scarcity. They're what allow you to do things. They're the thing that you as a player are generally consciously monitoring. I mean, lives is kind of the quintessential example. How many lives do you have left in Zelda? How many lives do you have in Mario? Generally 1, unless you get Super Mario, what have you. Vespene gas here is the second picture. That's from StarCraft. StarCraft and Warcraft and so on have an interesting system in the real-time strategy where you have 2 resources you're monitoring on the overt level. So you have like minerals and gas. That's like the obvious, here are the resources you have. But then you could also make the argument that there's a lot of other resources, like the strength of your army, the number of units you have, the defensive capacity of your army. Each of those could be considered resources, but on the most like just literal interpretation of the word, your Vespene gas, your minerals, things along those lines are your resources. Next up, we have gold.
Sorry.
Gold is your currencies in different games. I mean, again, obviously a resource. The last one, though, is pretty fascinating because this is the movie cover, but Prince of Persia did a really good job of playing around with this idea of what is a resource. In Prince of Persia, anybody ever play it? Yeah? No? Can you guess what the resource is there?
Oh, wait. Actually, I only played is it Sands of Time?
Any of the Prince of Persia games.
So Sands of Time, the resource was, or one of the resources was, you could like essentially replay what you would, like if you messed up, you could wind back time.
Right. Exactly.
But you could only wind it back like a certain amount.
So you literally had a little hourglass or whatever, a time counter that would fill up, and you could then rewind for a few seconds or however long based upon that resource. So they actually turned time into a resource in the game, and that was pretty wild when that first came out. Some other games have played around with this idea a little bit now too. Braid, for example, does rewinding of time. It's a really, really good indie game if you ever get the chance to play it. So yeah, resources. Objectives, all different sorts of stuff here. I mean, we got Zelda in the lower right. That's Link fighting a boss. A boss is probably the most obvious objective you can think of. Kill the bad guy. I think that's something we're all pretty familiar with. You've got matching games and kind of puzzler sort of games. You've got Battleship, where the objective is to sink battleships. You've got racing games, where the objectives are either beating opponents or beating times. So it's just a good idea to kind of think about formally what are the objectives of your game. It's really easy to be like, to win. Well, okay, does the player know what that means? Do they know what it means to beat a boss or why they're beating a boss? Or should they, be matching these points and doing what to achieve what? You need, without a sense of the player knowing what the objectives are, they're never going to be motivated to complete them. So, rules. They provide a couple key features. One of them is to close loopholes in the game. So, if you find that there's just a general problem with the way things are working, you can rebalance by adding a rule. And in that, along the same vein, they essentially provide balance. The way your rules work determine how the game is balanced, which we'll get to in a minute. This, to me, is pretty fascinating. Mathematics and game design. It's what we're going to be talking about a little bit as we actually look at the balance of video games and balance equations. Richard Garfield was an actual mathematician, and he designed Magic the Gathering, which is kind of known as a pretty intensely strategic game. There's 5 different colors you can choose from, and each have their strengths and weaknesses. If you know, for example, or if you're familiar with that little 5-color diagram on the back of the card there, you might be aware that the colors opposite to each other are enemies, and the colors adjacent to each other are allies. So that's kind of one example of the way rules are structured within the game. So red is enemy to white and blue, whereas allies to green and black. So you'll see things where, red versus white or blue have, more damage or more defense or something along those lines. So you can start to see that there's certain relationships between different classes or colors or whatever you want to call them in the game. And it's these relationships that it's really easy to just kind of be like, oh yeah, whatever, red is better than white. Well, no, there's equations that balance this. There's ways to think about these. Otherwise, without these linchpins and these equations, the game just falls apart. So, any questions about formal elements before we move on to balance? Okay. So balance. Taking a step back. Last time I mentioned that a video game, I think, is essentially an educational experience. And at its heart, a video game is teaching you something. You are spending the entire time there learning some skill. You might not know what it is yet, or you might not even care what it is. But the reason that you're able to beat the game at the end and not at the beginning is because presumably, well, okay, you might have acquired some new items and stuff along the way, but you've also learned the skills involved with those items, how to use them. Some games are more purely skill-based, like Flappy Bird. Somebody could hypothetically pick it up and win it on the very first go, or score highly on the very first go. Other games have more of a Zelda, for example. You actually need to unlock pieces to get to the later levels. But in either case, you still have actual skills that you're developing. So, thinking about human skills, this just occurred to me last night. I was walking home and I saw hopscotch drawn on the pavement, and it just struck me that hopscotch is a game that some kids invented sometime in our history to teach themselves motor coordination skills. Kind of fascinating to me because going back to the book I cited last time, Jane McGonigal's book about games and serious games and play and things like this, she makes the very strong case that play is fundamental to humans. And you can see this case echoed in a lot of different places by not just game designers, that the notion of play is how we experience and learn new things. I mean, look at dogs. Dogs, when you see them like batting each other and playing with each other, that's not frivolous entirely. In fact, it's very, very functional. They're learning the social order of how to interact, how to communicate with each other, and our children do the same things. So it's just kind of fascinating to me that hopscotch is this like organically brewed game. I don't think anybody ever sat down and said like, oh, I'm going to make the hopscotch game. It's going to go sell 1 million downloads in the chalk store. It's like some kid just drew some squares and they made a game out of it, and it served the purpose of kind of like teaching them motor skills, teaching them social skills, etc. So there's implicit skills in any game. And that's from that understanding, we start to understand a little bit more about how difficulty works and how it all relates to flow. So let's look at this graph. This is one of the graphs that I researched a lot when I was working on serious game design. This graph has to do with something called super memo. It's an algorithm that essentially determines how frequently you should represent information in order to prevent it from being forgotten. Another way of speaking it is that if I'm doing flashcards and you show me a flashcard and I'm like, okay, I got it. How long now do you need to show it to, how long before you should show it to me again so that it's shown to me at just the right time when I'm about to forget it again? And without going too much into the research here, though, it really is fascinating. I could talk more after the class about exactly where this comes from and all that sort of stuff. This is a whole topic of discussion in of itself, the human forgetting curve and stuff. Just kind of notice that after you memorize, there's this sort of asymptotic forgetting curve where it happens pretty quickly. And then each time you're reminded, you're doing a little bit better. That curve is a little bit less steep. And we start to see that all over the place. This graph actually is a graph of my own skill. I did this over the course of a year. These are actual data points when I switched from a QWERTY keyboard to a Dvorak keyboard. Everybody know what Dvorak and QWERTY keyboards are? Yeah, just for the sake of explaining. QWERTY keyboard is the standard keyboard layout that we all know and love. If you look at the top left of your keyboard, it spells QWERTY, QWERTY. So that's how almost any keyboard is generally laid out as you're used to them. There's many other forms of keyboard layouts, one of them being Dvorak, which was invented in the early 1900s as a way to presumably type faster. The reason being that QWERTY was not designed as a layout for speed or efficiency. It was designed to not jam typewriters. So the keys are not laid out in any sort of coherent manner as far as the goals we're interested in. Dvorak, on the other hand, was. For example, your home row, instead of being ASDFG, has your vowels on your left hand. And your right hand is your key consonants. There we go. So as a result, in Dvorak, you end up alternating left, right, left, right, left, right, left, right, much more evenly. And you end up reaching a lot less because the most common letters are right there under your fingertips. Anyway, I'm digressing here, but I did this graph where you can see that the blue line here is my words per minute typing with Dvorak, and the green was where I was at with QWERTY beforehand. And what I want to point out is that we've kind of got this same sort of asymptotic thing happening. There's a lot of skill progression right at the very beginning. I learned a lot of muscle memory in the first month or so, and then it just slowed down over time. So we see this happening in the human mind. We see this happening in the human body, where there's this kind of asymptotic relationship with skill, difficulty, time, that sort of thing. So we can use this insight to understand what it means to create a difficulty curve in a game. So we never want the game to be impossible. That red line would be very, very bad if we ever hit that point. Because if the player realizes it, maybe we can get by with and sneak it by him once or twice, but if the player realizes that the game is impossible, he's going to throw it away and walk away. So a properly constructed difficulty curve looks at their skill and translates that into difficulty. Now, as you get more skilled, the difficulty is actually going to increase less and less and less. We'll come back to this point when we look at how this is going to be implemented in the game we're building. In a formal declaration, we've got something like this. Your difficulty is your skill raised to the power of 1 over the some sort of constant plus the minimum difficulty. Something like that. I'm no mathematician. Two-curve balance, or more complicated balance, balancing different things against each other. So game equations, and when you design games, you should always have central variables. You should never have just like tons of little one-off equations all over the place. Rather, there should be constants that relate the variables together. So, for example, the easiest example is if you've got gravity, everything should adhere to the same gravity. Now, in our jumper game, anything that's falling in the game will have that same gravity, but anything that jumps might have more or less jump power. So it's important to understand, where are the things that are held constant through your game, and that keeps your game in check, sane, so that if you tweak that, it tweaks it worldwide, but also where are the things that are variable. So this chart is kind of, if you think about it in the terms of like a role-playing game or a MMO or something like that, you start off being rewarded very quickly and easily, and it's very satisfying in the very beginning. I like to think of this as like in an MMO, the gold drops and the loot drops from killing monsters. In the beginning, it's like, I killed a monster, I leveled up. And then it's like, okay, I killed 4 monsters, now I leveled up. Now I killed 16 monsters, and I leveled up. So there's this difference between what you're shooting for and what you get. As time goes on, the discrepancy between those two can become bigger. The player is much more willing later in the game to be like, oh, I'm going to work for 4 days to get this level. Whereas in the beginning, you better reward them pretty quick if you want their interest. So that's kind of how you relate the two, take these difficulty curves and relate them to rewards and things along those lines. So this is going to get a little bit practical here. So in the game that I've been building recently, for the past 8 months or so, it's actually very much similar to Magic the Gathering, as I mentioned last time. And one of the things I realized is that I needed to formalize play styles. I couldn't just say like, oh, these guys are going to have this attack power and defense power. I need to formalize it. So what do I mean by that? The dwarves are the red units, or the red race in Magic the Gathering, and I wanted them to be fast and aggressive. So what does aggressive mean? I decided to formalize that in terms of game balance, numerically. So the ratio of attack power to defense power is 0.7 for aggressive races, average, roughly. Whereas a defensive race, like the elves, the green units, is 0.5. So ratio-wise, the dwarves have a much higher attack to defense, and dwarves have a lot lower elves have a lot lower attack to defense. So in terms of gameplay, this is kind of interesting. You'll notice that the defensive quote-unquote units are still at a 1-to-1 average, 0.5. Anybody guess why I did that?
To make it more exciting? Let people attack more.
There you go. Exactly. I wanted people to be more aggressive by and large. I wanted the game to be fast, or faster than it was when I had it at a lower number. So by making it so that even a quote-unquote defensive race is evenly spread between attack and defense, it encourages you to attack more. Because you won't realize it consciously. You're not going to be sitting there like, ooh, 0.5, that means I should attack. No. What's going to happen is you'll be sitting there and realizing that if I don't attack, I'm not going to win this game. But that's because the mechanics are functioning in a way that are favoring the bold, so to speak. So, looking at our game here and what we're kind of using Doodle Jump as our inspiration. So jumping on platforms. If we think back to that balance equation that we were looking at recently, that asymptotic curve, we had two variables. We had the skill and we had the difficulty. So I just flipped to the slide with the answer, but does anybody want to try to guess what those relate to in this game? Like if we were to actually take these two things. Yeah.
I saw height on that.
Yeah, so the height is the proxy for your skill, or points, however you want to say it. In Doodle Jump, the height which you have achieved is the points, your score, or your skill level, essentially. In other words, as you get higher, the game should become more difficult. So what's the difficulty?
The spacing of the platforms.
Exactly. Yeah, so the difficulty is, well, right now we're only using one type of platform to start with, but the difficulty is how available are the platforms. On this screenshot, there's lots of platforms available, so it's pretty obviously quite easy. Over time, as the player gets higher, the difficulty should become harder. Now, this comes back to that asymptotic thing we were talking about. Think about when you're really, really far along. There's going to be just enough space that you're going to be able to get to the next platform. But if that moves by 1 pixel further, it'll become significantly harder because you're so far along that they're so spread out that 1 pixel makes all the difference in the world. Whereas in the earlier phases, some of these platforms could be removed entirely and it wouldn't make a difference. So the point is that the difficulty starts to change very, very, very little over time as compared to your skill level. So your skill keeps increasing, but the difficulty changes just tiny, tiny bits once you get far enough. That's the point of the asymptotic relationship. So, yeah, there we go. Height is your score, and platform spawn frequency is your difficulty. So, getting into a little bit of engineering now. This is kind of what the classical game loop looks like. Basically, most video games, probably 99% of them, have this function, this scheduled function that's called the game loop. It runs probably 30 times per second or something like that, because that's usually your frame rate. It doesn't have to necessarily be running at the same speed as your frame rate, but basically it's your updater. It's the thing that is changing what's happening in the game. So in our case, we need to be concerned with some basic physics, like the jumping velocity and acceleration of our character. We need to be concerned with things like collision detection when the character actually hits platforms. We need to be concerned with what? Losing the game. All of these things can be handled in the game loop. So something really interesting and is a common pitfall for first-time game designers with the game loop is that you always want the game loop to take in the dt, or delta time, as a parameter. And the reason for this is that you can't just assume even spacing. You can't just assume that it's firing precisely every 30th of a second. Instead, what you want to do is take that delta time and multiply it through so that if you're doing physics, you don't assume that a 30th of a second has passed. You take the delta time and say, okay, increase the height of my unit based upon the change in time. And that will make it so that even if your game lags or stutters or something like that, it still looks smooth because even if a frame gets skipped or something like that. teach me how to physics. So what we're going to be looking at, just for the basic code here that I've been working with, is initial velocity. That's kind of your jumping ability. I jump off a platform, and how high can I jump? Now in this first version, that's going to be just a pure constant. Just how much capacity to jump does the player have? In later versions, we might give him power-ups. We might tweak things based upon scenarios, like maybe one type of platform doesn't let you jump as high or something like that. It's a stickier platform or a bouncier platform, something like that. So that's one of our constants, one of our formal elements of the game. Now, we're all familiar with acceleration, the acceleration of gravity, negative 9.8 meters per second. We're not working in meters per second because we're in game space, so it won't be exactly negative 9.8, but the concept still applies. Basically, if I start with a velocity of, let's say, 10, to make it easy, that's 10, positive 10, so I'm going upwards in the y direction, so plus 10y. That means I'm moving 10 pixels per second in the y direction. Now, at the same time, we're going to be subtracting the gravity from that every second, or every dt, really. So if the gravity is 1, or really negative 1 in this case, then after 1 second, my velocity will have decreased from 10 to 9. And what you'll see is a really nice parabolic curve in the same way that you do when you actually jump in the world. If you jump off the ground, you start really fast, you slow down, and then accelerate down again. We'll see that when we actually run the application, play the game. And finally, collision detection. Collision detection we touched on a little bit last time. Basically, this is just the idea of two items in the game hitting each other. You can use physics engines, you can use some complicated stuff to do this, but we're going to do it our own, just for fun, see how it works, rather than relying on a physics engine. A physics engine can do some really cool stuff for us. Like, if we were using a physics engine, we would be able to say this platform is made out of rubber, and it would understand that for us, and it would do the appropriate things and change the way the world was working as a result. And they're actually quite slick, but let's work with something a little bit more basic so that we can actually understand what's going on under the hood. All right, any questions before we jump into code? Cool. All right. So here we are, the little planet prince. I have created a couple classes here. I've really just done some very, very basic modifications on the starting Cocos 2D project. Cocos 2D project, right? So I'm going to walk you through what I did just for the video here, and then I'll stop recording and we can kind of hang out and see if we can replicate it or do whatever you guys want to do. So the first thing I did was set up my scene. I left the intro scene in place, which is the one that has this menu. Go ahead and run the simulator at the same time so you can kind of correlate the code to the, Oh, thanks, Springboard. So I left the intro scene in place, which is really just our main menu, and that'll let us have this little hello world, play game, Newton physics. So what I did was replace the first menu item from, I forget what it was, some like little spinning sprite thing, into my new scene, which is called PP game scene over here. So very simply, I changed in the intro scene, I changed the text from whatever it said before to play game, and I changed the method that it calls, the selector in Objective-C parlance, to onPlayGameClicked, and renamed the method down here in the actual implementation, and I changed which scene it called to be PP game scene. pretty simple. Just replaced some stuff. PP game scene started as me just copying and pasting from Hello World scene, which was that spinning sprite that we saw in the last class. Now, there's a lot more code here. Not too much more, but a fair bit more. We still have the same sprite that's created right off the bat. I got rid of the rotation because we don't really care about that. And I actually created a subclass of CC Sprite called PP Player Sprite. By the way, PP Planet Prince. That's where that's coming from. It's just the prefix that I happened to decide upon for whatever reason, which actually kind of became confusing when it was PPP Player Sprite. But whatever, that's what I chose. All I did in my subclass, like, it's practically empty. There's almost nothing in it right now. The only thing I did was add a property that's a CG point property called velocity. CG point is a decent data structure here to use. There might be a better one, but I went with the point because it's, if you command click on CG point, you can see that it's a float X and Y. So that's really all we care about because we're building a two-dimensional game. Floats are good because we can multiply them through and have floating point math as opposed to just being integers. Even though ultimately the translations are going to be in pixels, it's still decent to have floating point math here. And that's really all I did, was just add a velocity property on this guy. So in the game scene, now instead of instantiating a CC sprite, I instantiate a PP player sprite. Eventually, the player sprite will probably have some stuff that does, some animations on him and makes him do different things at different times. So, yeah. Then I also created planets. This is the other subclass I created. Planet Sprite is also a subclass of CC Sprite. Actually, I did absolutely no modifications to this. It's really, I just created the subclass and let it be. This is just good bookkeeping down the line because we probably will want to have different types of planets. We're gonna, want to do some interesting stuff with that. So, yeah, subclassed CC Sprite for two different types of objects. So here we are, still in the init function. I now add some starting planets. So really, all I did here was create 10 planets. This method, if we look through, we've got a method called createPlanetAt, and that's taking a position. And the position I'm giving it is just random, arc4 random uniform, just a good randomizing function in Objective-C. It's really all you need to know about it, that it goes between 0 and the number you provided. So I just randomized completely these planet positions for the width and height of the screen. Self here is the scene, so it's the entire screen size. By the way, just speak up if you have questions or anything, because I obviously code in Objective-C a lot, and I might be skipping over things. So if I command click on createPlanetAt, look into this function, all it's doing is instantiating the, there's a little typo for you. Should have said planet sprite, not player sprite. But anyway, PP planet sprite, create it, instantiates it through this image, which is just this little bar right there, just a horizontal rectangle sort of thing. So instantiates it from that image resource. Anchor point is interesting. I think we talked about it a bit last time, but the values are from 0 to 1 in both the X and Y direction. And think of it like your sprite is a piece of card paper, and your anchor point is a pin, a thumbtack that you put through it. So if the anchor point is 0, 0, you put the thumbtack in the very, very lower left of the card. If it's 1, 1, you put it in the very, very upper right of the card. In this case, I set the anchor point to be 0.50, which means it's exactly in the middle horizontally and right at the bottom vertically. So I did that for both the planets and for the players. It's kind of like saying, it's useful for units, I find, that 0.50, because that's like where the center of your feet are, so to speak, the bottom middle. And then I set the position to whatever position I was provided to the function. Planets is a NS mutable array that I've created, and I just add it to that array so I can keep track of the planets pretty easily. Then I add it to self, which is, again, the scene. That's how it actually appears. Then I return the planet. Pretty simple. So far, we've created the player sprites and we've created the planet sprites. We've done all of our good initialization stuff. Now, lastly, I kept the back button in place in case you want to leave your game. The game loop. We schedule the game loop on once every 1 divided by 30 will give us 30 frames per second. Now, this actually is a little bit misleading. Cocos 2D is doing the drawing, so this isn't actually our FPS rate, but it's still a good idea to do your game loop at about the same rate as your frames per second, just so you're updating variables at an appropriate interval, if that makes sense. So schedule means that this function, game loop, is going to be called every 30th of a second. Schedule is provided by Cocos 2D, and it automatically passes in the CC time. CC time is really just a double. It's a type def. So just a way of referring to a time and being able to do decimal-based math on it. So let's start by just commenting out some of this so we can actually see some of this run without actually looking at everything I'm doing. You start, oh, by the way, I think I forgot to mention, I set the player's initial velocity to 0 in the x direction and k jump velocity. K jump velocity, I've defined 2 constants at the top here. Jump velocity is what you start with in terms of velocity going upwards, and gravity is how much is going to be subtracted every second. So it's going to take about 1.5 seconds, roughly-ish, really like more like 1 1/3 for the player to reach the zenith of his jump after jumping. So I commented out some of this, and just left the velocity and position in place. So the first thing I do is reduce the velocity in the y direction by gravity multiplied by dt. And the second thing I do is update the player's position based upon the velocity multiplied by dt. So what does all that mean? Play a game, and the guy went up and falls down. I just turned off all the collision detection, so that's really all there is. Try it again. Goes up, falls down. Pretty simple. Now we're actually going to have to reintroduce another feature here that I'll explain in a second. This feature is the fact that it actually scales up as you go upwards. Boom, 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 boom. Womp, game over. Missed the platform, fell off the screen. So I'll look at the game over case first. Remember, the anchor point on the player has a 0 as the y value. So what I need to do to figure out where the head of the player is to add his height to his position.y. That'll give me the position of the top of his head, the top of the bounding box. So if the top of his head is less than 0, remember 0 is the bottom of the screen in the y direction, then he's fallen off the screen. And if he's ever fallen off the screen, then the game is over. Pretty simple. But what was really interesting about that change we just did there was this notion of increasing the height. So this is actually what we talked about with regards to score and getting higher in the game, you noticed that the camera seemed to be panning with him as he got higher. You didn't want him to go so high that he got off the top of the screen. So what's happening here is I'm looking at the player's position in the Y and then subtracting the content height divided by 2. In other words, the player's position minus half the screen height. And if that's greater than 0, in other words, if the player is more than half the screen high, then we call this function increase height. Increase height first increases the score. It saves self.height into the amount. So we've passed the amount, which is how many pixels above the halfway mark he is. So height will always be, the self.height will always be the total displacement by which the camera has moved. And that will effectively be our score. Does that make sense to everybody? Yeah? Okay.
Do you always add the amount, or do you only want the max amount?
Because if you bounce on the same platform twice.
But this only happens, the increased height is what's panning the camera.
Oh, I see. Okay. That
Yeah.
makes sense then.
Yeah, so if we look at this again, see, he's
Yeah.
falling here. That's not calling increase height. Oh, wow, that's a fun one. Oh, that guy happened. Oh, the whole thing seems to be frozen. Recording stuff, so I'll figure that out later. Spawn planets is right now just being triggered on a 10% chance. And what it will do, so 10% of the time as the screen is panning upwards, it might spawn a planet. What it does is look through all of the existing planet, choose a random point on the screen first, look through all of the existing planets, and see if the new planet is going to be intersecting with one of those planets. If it is, then it chooses a different point. The point being that we don't want planets overlapping with each other. Preferably all of the spawned planets are at different places. So, yeah. Oh, and I don't randomize the height here. I spawn it at above the top of the screen. Again, recall our anchor point is at the bottom of the object. So if I pass in self.content_size.height, that means that the position of the object is just at the very tippy top of the screen, not quite on screen. Just like the bottom of the object is at the top of the screen. So it's almost like it's perfectly off screen when you pass in that height because of the anchor point. Yeah, that spawns the planet. Oh, then the only thing that I forgot is that I changed the touch handler code here, which is just when you touch on the screen. Right. Simple solution. So one other thing we could do in here that might help it out a little bit is make it so that they never get spawned so tightly packed together. So we can improve the spawners a little bit if we were to make it so they don't spawn quite so off screen, and if they don't spawn quite so